I like about mathematics is the notebook. It's absolutely ideal. There's a fairly typical set of calculations, and it's nice to be able to use the finite elements in Mathematica, in the calculation, without having to go anywhere else. And I actually got Mathematica version 4, which is in 2000 or 2001, and that was a revelation. But the graphics in Mathematica are superb. Although it took me a little while to get into Mathematica at the time, I never looked back really.
Hello, everyone. We are today here with Malcolm Woodruff. He's a civil engineer and he's an enthusiastic user of Wolfram Mathematica over the years. And first of all, I'd like to thank you, Malcolm, to be here. It's a pleasure to have you here.
Pleasure to be here.
Before we start talking about all the cool stuff we have been doing with Wolfram Mathematica, I would like to use this opportunity to get to know you a little bit better. Could you share with us a little bit of your background, a little bit about yourself, so that we can know a little bit about you first?
Okay. I started work as a junior site engineer on a power station site in Kent in the UK in 1967. So it was rather a long time ago. I then worked for a river authority, for a water board, whilst I was studying. And then when I completed my, or the equivalent to a degree course, I worked on flood prevention works for Milton Keynes Development Corporation. I then went to a consultant working on sewage farms, or design of sewage farms, and I did all the structural, ended up doing all the structural work in that company. Whilst I was there, studying for a master's in civil engineering structures, and then in 1979, I started my own company, working as a consultant in the south of England. Since then, I've done a varied amount of work, mostly in the structures and civil engineering, but also in geotechnical engineering, where I did most of my work, happened to be the biggest landslide that's inhabited in Europe. So it gave me a good chance to do a lot of geotechnical work. And I ended up doing a lot of stabilizing work for landslides and building on landslides, etc. I class myself as a civil engineer, and to me, a civil engineer does everything apart from guns. But I have done the odd submarine and warship, but they were for museum projects. So I think they still count.
I see.
I can show you a little, if you like, of the sort of things that I've been doing.
Oh, please. That would be nice.
Okay, let me share the screen. This is a simple job, which I was quite pleased with. It was in a dry dock where the existing is a Victorian structure, and the existing supports to the a travelling crane, which you can just see in the corner there, were rusting out. So I designed a replacement using hollow sections to support it. And I was quite pleased with it because it looks better than the original. And it took about 15 minutes to actually change each one of these posts. Which,
So this was to sustain an existing construction.
that's right. The traveling crane still runs on the top. Okay, the beam actually holding it between the posts was okay, but the posts themselves and all the lateral supports to the posts.
And I can see that only this structure that is in the middle of the photo has some diagonal
Yeah,
structures as well.
yes, just the central post
Oh yes.
is joined naturally, and I did that so that the top beams could expand due to temperature and not
Hmm.
be stressed. They were free
That's
to do it.
it's like that's something we see on bridges when we ride through them with our cars. We feel that there's some gaps.
Yeah, yeah. If I put the raking struts in at the ends, then it would have stressed the bridge because it had been held at 2 points. Holding it with 1 point allows it to expand.
That's really interesting.
So it was a very simple job, but it was a nice one. I was quite pleased with that.
Okay.
This one is on the Isle of Wight. It's a marina, but a new build where they put houses on the marina and then they berth their boats next to their houses. So that was quite good. Done very much to a strict timetable.
That's really nice.
I think it was less than a year from conception to completion, which is quite nice.
Yeah.
I've done quite a few houses, so not all the jobs are big like that. Um, that was a Decker house. It's 10-sided, all steel house, which was unusual. It was
Yeah, it's pretty nice. I mean, it looks like an upside down house.
yes, yes. I've done a couple of sort of mushroom shaped ones. They seem to work in.
Oh, mushroom shape. Yeah, I can see that.
Um, this one is a house where it's quite a big house, and the architect very cleverly designed it so there was no low path continuous from top to bottom. Um, as you can see here, the post comes down onto the floor.
Yeah.
There was in that floor as well, and that was like it all the way around. The only way to design it at the end of the day was as a concrete structure with a brick out of the skin. That is just part of it from underneath. Yeah.
Do you have those let me see, like those square gaps?
Makes the floor much lighter.
Oh, I see. So you remove mass from that part so the structure is not heavy.
That's right.
That's nice.
Yeah. This one is a airport I did in Northern Ireland. We did about 3 jobs. Well, actually, we increased the length of the runway at one end, then the other end, and when we took it, actually, the idea was to take it up over the railway line that runs along there and out into the dock. But there was a problem with the environmentalists because there was birds nesting up and and just before we went out on the lot, we were told we couldn't do it. So the council bought the properties that ended at the other, that were under the runway at the other end, and they extended out that way as well as that way. We also did the taxiway out to a place here where we put an apron up. Again, that job was, I think we actually got it at the beginning of November. No, October. Got it in the middle of October, I think. And it was complete by May the following year.
That's nice. I think it seems like a quick job, right?
It was a quick job, yes.
Yeah, for a civil engineer, I think that
Too quick, really.
too quick. Yeah,
One of the problems that we had on it was extending the runway here. The ground conditions were there were 40 meters of what they call sleech, which is glacier lake deposits that are very soft. So we were expecting a lot of settlement, and the fact that the embankment that we're building to put the runway on is 150 meters wide, means you do get a lot of settlement, even if you're only increasing the height by a meter or a meter and a half.
I see.
So we had, in those few months, we had to actually build up that area as high as we could to increase the speed of the settlement. So, and then we had the railway. We also had a river that went along here, drained this area, and some mountains to the south.
I see.
And
So there's a lot of environmental factors involved.
yes, this was part of taking the river underneath the runway. And a job I had on the Isle of Wight again, there's a existing lift shaft that takes people down to the beach to the left, and the bridge was corroded, so it had to be replaced. So I designed this bridge, and also built some protection for them and so on, which was quite nice.
Yeah.
Other houses. This house was in Seaview. There's a road there where most of the houses are affected by the movement of the slope, coastal slope, and failing, the slope failing, existing houses getting damaged. Here, the existing house was taken down and we built this one instead. Holiday home.
By looking at your very nice examples of your past jobs, I keep wondering myself, where does computation comes from in these kind of projects? Do you have like stress simulations, thermal expansion simulators, simulations? Do you have some? Do you use something like this for this kind of projects?
Well, I have a structural analysis program that calculates the stress through the loads. It's basically a frame analysis program, although it can do two-dimensional finite elements.
Okay.
Yes, I use that to do the initial stress analysis. Having said that, I'm currently writing one to be able to do the same in Mathematica, because I don't see why it shouldn't be done in
Yeah.
Mathematica. So
Yeah. Something that's
something that's coming, maybe, hopefully by the end of the year.
yes. And by that hook that you just gave me, I know that you have a book about an introduction to Mathematica for civil and structural engineers.
Yes.
And I would love to ask you, what was the motivation to do that book? What happened between the first time you thought, maybe I should write a book about it, and the actual book being released?
Well, one of the things that I'm very keen on is you need to prepare calculations for any structure that you do or any job that you do. And to do that, you have to gather information. You have to detail your assumptions that you're making, the standards that you work to, and then show the calculations, and they should be complete, so that you can come back to them 10 years later and see what you've done. Those often need to be checked under building control. They should be checked if it's a building, but certainly if it's an important structure, then they ought to be checked by somebody else. And
You mean as a recheck, a double check?
as a check, to check that you've actually got your calculations correct and the structure's going to be safe and
Okay.
going to do what it's supposed to do. Now, I used to check calculations for a council that were submitted. I still do checks for stability work, geotechnical stability, that is. And a lot of the work that I see is not very good. It's not presented very well. You can't follow it very easily. It tends to be scribbled calculation sheets done with a pencil with annexed bits of Excel or calculations that have been done on a calculator and just written the results to. Or what's sometimes actually worse, you get some of these programs that to design you a retaining wall.
I see.
May be very good and give you correct results, but because they want to actually cover themselves for every possibility, you get 10 or 12 sheets for doing something that you ought to be able to do in one sheet. And it makes it very difficult to actually follow and understand what's going on.
I see.
So you need an environment that you can actually tell the story, get your calculation to tell the story. I could show you one if you wanted.
Sure.
Um,
I mean, if I understood you correctly, by doing that kind of job as to check other engineering's calculations, you noticed that there was like a lack of they're using like proper tools for doing those calculations, right?
yeah, they might be using proper tools, but you can't follow what they've done.
Okay, I see.
Or whether they follow what they've done.
So they should be both correct and pedagogic, so to say.
Yes. Yeah. Let's see if we can do this.
And that's probably where you thought, maybe I should write a book to show civil engineers this nice tool I've been using.
The tool that I like about mathematics is the notebook.
Yeah.
It's absolutely ideal. All right, I'll show you one that I've done here. Let me share the screen again. I've done this. I redacted some of the ship names and so on because it was for the Admiralty, and I'm not so sure how happy they would be publicising everything. Okay, this is calculations I submitted for repairing some piles to a jetty. So they were written completely in Wolfram's notebook, but then printed out as a PDF. So this is the PDF.
Okay.
Apologize for the. It does mean you can, in actual fact, use the hyperlinks that you use in the notebook. They go on to be able to be used in PDF, which is very useful.
I
So
see.
they're the contents. Propose what we're trying to achieve, drawings that I was working to, references that I was working to, design assumptions, and here I'm starting to put information in. Tidal levels there, for instance, survey results that I took from document that was given to me, and design ships that I use. I was able to just drag information in, put them into my calculations. It's super thing to be able to do. Drew a table up, and then worked out the calculations for earthing forces. So a little bit of arithmetic, and then I drew up this manipulate, which works the energy absorbed by a fender for the deflection of the fender, and then the force that is transferred through the fender to the structure.
Wow. Pretty nice.
So that's the calcs to get it. And that's an example. And by moving the slider for the deflection, where it intercepts the two curves, it gives you one reaction and the second the energy that was absorbed. So I did that for all the ships.
Really nice how you can like create a story and at the same time show your calculations, right?
Exactly. And if the calculations are too involved, you just close them. You so they're still there, but you can't see them. They don't interfere with the story, but you can always get them back. That's a very useful thing because just doing some of the graphics, you get a lot of options to show the colours and what have you, which really are not necessary at all. But you can hide all of those.
Yeah.
That's good. So working out the loads on the piles, check on the existing, getting information in about stresses allowable on the greenhouse piles, then working out the additional forces. And here I've used finite elements to calculate the forces actually in a pile where it's supported at the top. were partly supported. It's just a rubber support onto the jetty, and it's embedded in the ground. So that's all my calculations for the.
Wow, this is pretty nice. I mean, this figure on top, it looks like network, points network to distribute stress. Is that something like this?
It is. It's the mesh through which you're actually working out the stresses on. You can't see it on the pile because they're so close together. But
Yeah,
on the ground where you can spread it out more.
that's nice.
These are material parameters, boundary conditions. Then you solve it for deflection, and you gives you a nice displacement curve from which you can work out the bending moment. Do that for all of the piles, and then you can produce a table. Then, because these were splitting because they were old and been overstressed in the past, we wanted to put sleeves around the ones that was necessary. So I ran the finite element analysis again with the sleeve. Saw the differences that the sleeve made, and then actually calculated the stresses on the clamp.
Wow, it's really nice.
So this is
Wow, look at this.
the clamp, and that's the deflection on the clamp with the stresses actually painted over it. And then basically summarized it all. There's a fairly typical set of calculations, and it's nice to be able to use the finite elements in Mathematica, in the calculation, without having to go anywhere else.
Yes, you don't have to do your calculations and then merge together to a project. You can write everything at once, so to speak.
Yes.
And how long does it did it take you to finish this project, for example?
A few days' work at most.
Okay.
I did look at the scheme earlier and drew up the whole thing. We were going to replace the fenders and the fender backboards. And then we decided that we would actually repair the piles. So came at it again. A few days.
I see.
Yeah.
And you told me in our first conversation that you have used Wolfram Mathematica since the very first version, so to speak. Do you remember which one was it?
It was version 2. But no, I haven't. Version 2, I got hold of a copy. I had a good look at it and decided I didn't understand it.
But why did you get it in the first place?
But
The first.
I needed to be able to do my calculations better than using programmable calculators or computers and basically doing them by hand.
By hand?
By hand. Yeah, I saw with a slide rule, so yes.
But where did you hear where did you hear about Mathematica in the old days?
Well, I can't remember. I looked for it, I think, and I knew it was the sort of thing that I needed. But it was too complex at the time because it did not do mathematical notation. And Therefore, I actually chose MathCAD. But MathCAD was, compared to Mathematica, is very limited. It only works on the PC, and I preferred to work on the Mac. And by 91, I think,
Okay.
by 98, it was
Okay.
no longer available on on the Mac. So I started looking around, and I actually got Mathematica version 4, which is in 2000 or 2001, and that was a revelation. Not only was the notebook interface so good, but the graphics in Mathematica are superb.
Yes.
And although it took me a little while to get into Mathematica at the time, I never looked back really. Very happy with it. I used it as a calculation pad to begin with, and then started writing programs in it. Again, writing programs in it is quite straightforward because you are still using mathematical notation. You can still follow formulae and that are in codes of practice. It makes life so much easier. And to say the graphics are great.
And after that many years, I mean, you have been using it for maybe many decades, right?
Well, 2.5 years.
Yeah. Yeah. It's amazing. And you recently published one book, which is really nice.
Yeah, well,
There's something that took really got my attention was when you show like a picture. Maybe I can show it here. I'm not sure if I have it open, but I have. You show it like a satellite photo of a place near the beach, and then you show it like the 3D landscape of that photo.
I can show you some of those. Yes.
I thought it was amazing because I was so used to have like just see like 3D graphs or something like this that I never thought about using that function to visualize like an actual place.
I've got it here. I think if you want it.
Yes, if you kindly can show to us, it would be nice.
Uh,
There should be like a badge for people who are like using Wolfram Mathematica 6 version 2, so people would know.
mm,
Yeah, exactly that kind of. I find it's really amazing.
yeah, but this one is actually from an IDA survey. Place where they wanted to build actually on the coastal slope for some reason, and to design some stabilization works. So I got a survey done, and you can imagine it's a huge amount of data in it.
Yes.
But once you've got it in, you can play with it quite happily.
Yeah.
This one is um, a, a job um, where I've taken the LiDAR data in, I draw a contour plan. Same with this one, that's another one.
Yeah.
But I can output that in 3D. That's a relief plot. The relief plot is very good. I'll show you another one in a minute. That's that area contoured, and then put a photograph over it.
I would I think this is fascinating, like a 3D photograph of the actual height of the terrain.
Yes. As I say about the graphics in um,
So it seems like a merge of the actual satellite photograph of that place with the actual points with the different heights for the location
exactly
combined,
that.
right?
Yeah, exactly that. And on this one, they're exaggerated a little, but that's through choice. It doesn't have to be. Um, I've got another one here. If I can. Oh, that's the Art of Light relief plot.
I
So, Wolfram Mathematica. Um, just as a matter of interest.
Nice.
Yeah,
There's something about pressure. There's a very coloring pressure diagram below. Take below the rainfall. It's on it.
yeah, that's finite elements. If
Oh, and this something that
no,
really strikes me is because pressure is negative.
yes, yeah, that's the pressure on a circular tank, um, which is in my book on finite elements that should be up in the notebook archive any day. Um, it's there. It's ready to be published.
It's really nice.
Mm. And
Wow, look at this.
that's the circular tank, greatly exaggerated, settling into the ground. So that's where it started from, and that's where it ends up. But as I say, exaggerated. But it's not to exaggerate these things so that you can actually see what's going on. Um, and then you can do slice plots, um, contour displacement underneath. That's without
But do these kinds of graphs that you're just showing to me, do they help you just visualize what's going on in the problem and or,
exactly.
or do they actually provide um
They provide answers.
information?
Yes, they provide answers.
Okay.
Here, for instance, the contours showing the stresses, um, and this is a legend showing the stresses for these contours. So
I
you can
see.
take those.
So it's not a homogeneous stress.
There's no homogeneous stress. No,
What are those two white? There are no
that's
stresses in
and
that?
the stresses are out of the scale that you're plotting.
Oh, I see.
So I could get those stresses in, but then you'd lose a bit of detail
Sure.
as well. And that's the same thing um,
Wow.
in the other direction. And these are all standard Mathematica plots. Um, very easy, very easy to do.
Wow, very big stresses, 10 to power 6.
Yes, but they're in Pascal, so that's
Okay.
with it's okay. Um, but yes, let's see. Yeah, that's-
And is this looking just for a particular component of the stresses? Like I can see in the figure below is sigma xx. Can you see like the full stress tensor of this if you want?
yes. Well, that's the one minus stresses, which is the combined stresses.
Oh, the combined ones. Okay.
Yeah, but
But if you want to look at the stress in a particular direction,
I can do, yes.
oh, I see.
Yeah, it's not a problem. But that there is actually the stresses from this anchor block. This is an anchor block that we put in to stabilize some ground. with ground soil nails in, with very high stresses coming in from the soil nails. So
It's nice that this cross-section stress, you have both tensile and compressible stress in the same structure, both
yeah,
positive and negative stresses.
yeah, yes,
It's really interesting.
we'll do that. This one is just from my book, which is stresses in a V-shaped beam for a footbridge. And that's actually you want to manipulate, so you can actually work your way along the beam. Oh, God.
So help me understand just a little bit better how to obtain, for example, this particular plot of cross-section. What is the process? You have the data of the cross-section.
Right, I'll show you that one.
Just what is the process to achieve a
Yeah,
figure like this?
right, I'll show you. Bolt part of the anchor block in from a CAD program, and then meshed it, put in the boundary conditions,
Okay.
markers, and then solved it using the boundary conditions and solved it using finite elements to work out the stresses. Then that gives me the stress painted on the face of the model. That's the whole model with the one minus stresses painted on and showing the deflection. Again, greatly exaggerated.
Okay. Oh, I see.
And that is all I need to draw those sections.
So you get the forces that are being applied, and then you get the structure you wanted to analyze,
That's right.
and then you use finite elements to create to generate the stresses.
Yes.
But those forces that you showed, like in the beginning of this document, which was like in the range of kilonewtons, right?
Yes.
Uh, are those forces like standard, or they were chosen for a particular reason?
I first started by designing the stabilizing works and finding out what forces I needed to stabilize the ground.
Oh, I see.
And I did that in a program called FLAC. The finite elements in Mathematica, they're coming on. They're very good for structures and very good for this sort of thing. But they are not to the standard yet of a program like FLAC or Plaxis that is designed purely for soil mechanics.
It's really nice.
But there again, last time I upgraded FLAC, it cost me twice what I would pay new for Mathematica.
I see.
So, you know,
And this is like, um, I have a final question for you regarding the use of Mathematica, actually. Why, in your opinion, should civil and structural engineers today consider learning and using Mathematica? What do you think what would you highlight as its main advantages?
the ability to gather all the information you require in the notebook, do the calculations, summarize it, and present it. That is sort of, I think, probably the main thing. But also, it actually enables you to do work that I think you'd find it hard to do otherwise without investing in a lot of programs. And then you had the job of presenting what you're doing. I think it's very cost efficient. As I say, to get a solid finite element program, you'll probably pay at least as much as Mathematica on its own, and maybe twice as much, depending what you go for. You can build yourself a set of functions to do all your day-to-day work very efficiently, and it's very easy to do. Yeah, you do need to sit down with it for a few days and actually see how it works for you. But that was the idea as a book, that by giving examples of how you can use it, it gives you the confidence to get going on it very quickly.
Since you have been using, since your first contact was in Mathematica version 2, but then you came back around version 4, something that I know it has been done in Mathematica is that if you get, I'm not sure which version you're using today, maybe 14.3 or something like this. But if you get like the old notebooks from version 2 and 4, they're still gonna be good. You can still open them and run them on the current version of Mathematica that you have.
Yes, you can.
Have you tried those?
Oh, yes. Yes, I do go back to that now and again. And yes, it's very good. Whereas the MathCAD programs that I wrote in MathCAD, or functions I wrote in MathCAD, I can't open it even. I can't look at them.
Yeah.
Um,
This is something that we get for granted in Mathematica, but it's I assume it's not that simple to make that work.
no, I think it's part of the original scheme of things. It had to work on everything.
Yeah.
PCs, Macs, Linux, and it works, and it works very well.
Yes.
And because it's actually a text file, not that it looks like it, but that's all it is, you can open it with a word processor as well.
Yeah. It's really nice.
It is
And
really nice.
before we wrap up this nice interview, you're finishing a second book, right?
Yeah, the second book is on finite elements, and it is actually finished. It's with Wolfram. They should be publishing it on their notebook archive. It was sent to them just before Christmas, so I'm hoping it's going to be published very soon.
That's nice.
But that,
And
again, helps people get confidence in using the finite elements.
for making some examples, like you just showed me, like to calculate the stresses.
Yes.
It's really amazing. Malcolm, it was fascinating to have the opportunity to talk to you and learn a little bit about your history. I learned a lot by talking to you today. Thank you very much for that. And thank you very much for agreeing with this nice interview.
Okay. I hope more engineers make use of it.
I hope so too. I hope a lot of engineers see these videos and say, oh my gosh, there's a better and nicest way to do what I have been doing in my life.
Yeah. Good.
So thank you very much.
Okay, and thank you.